Alright, welcome to our very last video. This video is over conditional probability. So before we begin on conditional probability, let's go ahead and take a look at this table. We'll be using this table over and over and over again for the next several examples. What we have here is we have aged broken up from 18 to 29, 30 to 64, and 65 and over. We also have marital status as married, never married, widowed, and divorced. So this is one of our two-way tables that we discussed in the previous video. So looking at this table, if A is young between 18 and 29, what is the probability that you are young in this table? So we have 22,512 young people out of 103,870 people polled. So that would be this fraction, 22,515 over 103,870, and as a decimal that would give me 0.2167. Alright, what is the probability that you are married? So let's take a look at the married row. We have 59,920 married people out of the total polled, so there's your fraction. So typing that in your calculator, that will give you the decimal, 0.5769. So if A is young and B is married, what is the probability that you are both young and married? Okay, how do we know that being young and married are not independent? Well, first off, let's take a look over here. Remember that the probability of being young and married must be equal to the probability of young times the probability of married if they are independent. Okay, going back to the table, we look at probability of being young and married. Here's young and married. So we would have the fraction 7,842 over 103,870. Okay, and that's going to give us the decimal 0.0755. So let's take this number as well as the probability from here and here to determine if we are independent. So the probability of A and B both being young and married, let's erase that and try again. Okay, is 0.0075. Is that equal to the 0.217, the probability of being young, times the probability of being married, 0.577? And the answer to that is no, they are not equal to each other. Therefore, they are not independent. Being young and being married are not independent events. Alright, and on this page we have a new notation. You'll see this little line here. That's read as given. So what is the probability of A given B? So what is the probability that I am young given that I already know I am a married person? So I want to know, out of all of the married people, given that I am married, given B, okay, so I'm not going to be any of these people because these people are not currently married. This is known as conditional probability. Okay, given something, we are narrowing down the perimeters. We're not looking at the whole group, we're looking at this subset of married people. So given that, what is the probability that I am young? So our fraction is now 7,842 over the 59,920, not over the total amount, because this total amount includes not married people, widowed people, and divorced people. So 7,842 over 59,920, that's going to be equal to 0.131. Okay, so the probability of being young, given that I'm already married, is 13%, or 0.131. Alright, so let's say that you don't have a table to follow. Take a look at this here. The probability of A given B is the probability of A and B over the probability of B. This formula is actually given on the formula sheet. So let's use this with our previous example. So I'm going to copy this, copy that, and bring that over here. Okay, let's make it a little smaller. There we go. Move this guy out of the way. So what we have here is that the probability of A given B, the probability of A and B is 7,000, excuse me, let me erase that. Boop. Okay, get rid of these as well. So the probability that I am married and young is 7,842 out of the 103,870. So 7,842 over 103,870. That is the top part of the fraction, probability of A and B. Now, probability of B was the probability that I'm married. So now we're looking at this total, 59,920, okay, over the total 103. So 59,920 over the 103,870. Okay, if I were to type this into my calculator, I'm still going to get the 0.131. Okay, notice how these are the same. That's because we use the formula here, or we use the table here. So it really just depends on what you've been given, on what you should use. Alright, so what is the probability of being 30 to 64 years old given that you are married? So we are looking at this section here. We are looking at the married folks. What is the probability that I will be 30 to 64? So we're looking at 43,808 people out of 59,920. And that's going to be equal to 0.731. Alright, so let's take a look as a refresher of the multiplication rule. Remember, if two events are independent, then the probability of A and B occurring is the probability of A times the probability of B. Well, what happens when we have dependent events? Well, we have another formula, and we can actually use it for any two events. We can use this for independent or dependent. And the reason for that is because here, this conditional probability, remember that independent events have probabilities that don't affect each other. So probability of B given A and probability of B will be the same for independent events. It's when we get into dependent events that it starts to get a little bit different. So this is the formula that we'll use, the probability of A times the probability of B given A. Alright, so let's take a look at that here. Probability of being young and married is 7,842 over 103,870. What is the probability of A and B? Okay, so the probability of being young and the probability of being married given that you are young. So the probability of being young is going to be 22,512 over 103,870. And we're going to multiply that to the probability of married given young. So let's get a different color, okay? Given that I am young, so given this group, how many are married? So that would be 7,842 over 22,512. And that's going to give us the same fraction, 7,842 over 103,870. Notice that this fraction is exactly the same here. Okay? So that's what we were looking for. Alright, so let's go ahead and take a minute to organize our thoughts. Remember that if I have the probability of A and B, I have two formulas, one for independent and one for dependent. And really what we can do is we can change this dependent and we can write any event. Okay? Any and all events, because this could be either independent or dependent. So if you're not okay with remembering two formulas, you can just remember this one because this formula will work for both independent and dependent. The top formula only works for independent, however. Alright, take a look at or, if I have the probability of A or B. So we're looking at mutually exclusive events, or also known as disjointed events. We have the probability of A plus probability of B. And the reason that works is because there's no overlapping. Remember that disjointed events do not overlap, so there's no need to subtract anything. All events are going to have the probability of A plus probability of B minus where they overlap. And that's because when we count A and B, we accidentally count this intersection part twice. Now again, this formula actually works for both disjointed and non-disjointed events because the probability of A intersection B on disjointed events are going to be 0 or empty set. So really, we're just subtracting 0, and then we have this formula up here. So the two key formulas that you really have to know are these two, okay, because they can work for any event. It's your job to remember, is it and or is it or? All right, so what does that look like in an example, okay? So let's say the probability of it going to rain is 0.4, while the probability of being left-handed is 0.3. These are independent events. Being left-handed does not affect whether it's going to rain today. Whether it rains today will not affect my probability of being left-handed. So we follow the multiplication rule of 0.4 times 0.3 to get 0.12. So that's the multiplication rule of independent events. Okay, let's take a look. What is the probability of B given A? What's the probability of being left-handed given that it's going to rain? Well, it's still going to be 0.3. Okay, because the chance of rain doesn't affect the left-handedness. So if I look at this, the probability of A times the probability of B given A is still going to be 0.4 times 0.3. This 0.4 and this 0.3 will still be the 0.12. Because conditional probability does not affect independent events. Independent events will have the same probability because the probabilities don't affect each other. That's the definition of independent events. Alright, that is our very last video, folks. I will see you guys later.